Alright, so in this video, it's just the motion of a particle moving along a straight line under uniform acceleration is shown below. So here we're given an x at t graph and the vertex of this particular graph, okay? And it wants us to find A, B, C, D, and E. Pause, read. Alright, let's do it. Let's keep up. In order to find the first answer, part A, calculate the average acceleration, the first strategy that you could imply, or that you could exercise is the average acceleration function here, which is final velocity minus initial over some sort of change in time. So it's up to you where you start, but I'm just going to go ahead and pick from 0 to 3 seconds because the vertex is given to us. So I'm going to start at 0 second and go to 3 seconds, okay? So at 3 seconds, it says the position here is at 28. Now, well, you need final velocity and you need initial velocity. Well, why would I want to start at 0 and go to 3? Because I know at 3, at the vertex, the tangent line here is perfectly flat, meaning the velocity is 0. So in order for an object to change direction, so as you can see on the graph, at times equal to 0, the object is at 10 meters, and then it kept going up, aka to the right, and at 3 seconds, it came to a stop, and then all of a sudden it moves leftward, okay? So I like to go ahead and go from 0 to 3 because of this particular vertex. Alright, so if I do that, my VF here is going to be 0 at 3 seconds. My VI, I don't know what it is, and then my change in time here is going to be 3 seconds. I do want to point out that it's important not to assume that VI is 0. How do you know if VI is 0 or not? All you have to do is extend the graph itself and cross the vertical axis. If you can draw a tangent line that is not flat, it is implied that the object is initially moving to begin with. Well, how do you know if it's moving left or right? Well, all you have to do is look at the slope. If you draw a tangent line like I did here, that tangent line is a positive slope, meaning the object is initially moving rightward to begin with. It wasn't stationary, okay? So do not assume object starts at rest. All you have to do is extend the graph itself across the vertical axis, and if a slope exists, then initial velocity exists, and if it's negative slope, then it's moving leftward. If it's positive slope like the one I have here, then it's moving to the right, okay? Alright, well, how do we know what that VI is? Well, all you have to do is use your kinematics equation. You can set up the two average velocity functions because it says here uniform acceleration, okay, meaning a is a constant, so you can use these functions. Well, displacement over time is equal to final velocity plus initial, or initial plus final. Doesn't really matter here which term you write first in the numerator because you're doing addition, divided by 2. So, well, how do I know what my values are, right? It's not bad at all, okay? Well, my initial position here is given as 10. At 3 seconds, the coordinates here says 28, so I just kind of went left here and I listed 28 for you. Well, during the 3 seconds, how far right did it go? Right, we know that it went to the right because the graph kept going up on the vertical axis. Well, from 10 to 28, that's a difference of 18, right? So I'm just going to plug and check here for you. Well, delta x, you can break it up into xf minus xi, xf being 28 on the graph at 3 seconds, xi being 10, a positive 10 here, because at 0 second it's already on the vertical axis. And then what's my change in time? From 0 to 3 is just 3. Well, VF here is 0 because at 3 seconds the tangent line is perfectly flat, right? So therefore it's 0. So once again, I like going from 0 to 3 for this graph because I can use the velocity at 3 seconds as 0 because it is. Well, the only thing I have highlighted here is VI, which I don't know what it is, and the 2 remains because that's part of the function. So if you do basic math, 28 minus 10 is 18, and then the 3 stays on the bottom there. And once again, 18 divided by 3, which is 6, and then you need to still get rid of this 2. So this 2 being on the bottom, you need to multiply both sides by 2. So if you do that correctly, 18 divided by 3, which is 6, and then times it by 2, which is positive 12. Okay. Alright, so that is the initial velocity. Okay. Now, once you have that, you can just plug it back into the average acceleration equation, right? The only thing we don't know is the initial velocity, but we just found it at being positive 12. So negative here stays because that's part of the function. So it'd be negative 12 meters per second divided by 3 seconds, which will give us negative 4 meters per second squared. And that's our answer for part A. So using the strategy, that's it. Now, I do want to point out though, by doing this, you actually found the answer to part B as well. Part B wants us to calculate the initial speed, or aka the absolute value of the initial velocity, right? The only difference here is speed, which is just the magnitude. Well, we found the initial velocity to be positive 12 meters per second. But because it asked for speed, I'm just going to box the 12 meters per second because I don't need the direction. So we already knocked out part A and B, okay? Now, I think this is the easiest way to find A. However, if you want, you can complicate things and do it this way. Well, you can apply the displacement function because you're given an x of t graph, right? Well, I know my displacement for the first 3 seconds is 18 because it starts at a position of 10 meters and then it went up to 28 meters before it turned around. So delta x here is 18 because 28 minus 10 is 18. Well, what's my VI? I don't know. Once again, do not assume it's 0 because the tangent line here exists. So I know it's some positive number, I just don't know what it is because it's not given to us. Well, what's my change in time? I want to plug in 3 because I'm going to go from 0 second to 3 seconds because I like the vertex here because it tells me my final velocity at that point is 0. On the right side, 1/2 gets carried down. The A is what I'm trying to find, so that's my unknown. Well, how much time? 3, and then we're going to square that. So as you can see, the only thing that's holding us back is the VI, right? So we need to still figure out what the VI is. So you're kind of forced, quote unquote, forced to go through the average velocity functions here, right? So once again, delta x over delta t equals VF plus VI divided by 2. You know, VF is 0 because I'm going at 3 seconds because the tangent line is flat. And then XF here is this, excuse me, delta x is just XF, which is 28, minus XI, which is 10. And then VI, once again, is only our unknown here in the average velocity functions. And if you clean that up, once again, 28 minus 10 is 18. 18 divided by 3, which is 6. And then multiply both sides by 2. So 6 times 2 is 12. Okay? So the average, the initial velocity, once again, checks out to be 12 meters per second or positive 12 meters per second. Now, once you have VI, you can just plug it back here, right? We want to keep A as our unknown. Well, I'll carry everything down, and then all I'm going to do is I'm going to substitute out VI. So instead of VI, I found what it is, which is 12. So here, we really, if you look at it, it's the only thing that's unknown is just A. So hopefully your algebra is on point. Here's 18 on the left side. 12 times 3 is 36. So you need to combine like terms, right? The 18 and the 36 here doesn't have an A. And then here, 3 squares 9. 9 times 1/2 is 4.5. So if you do basic math, the 18, you're going to carry this 36 to the other side. So you have to change sign. So it'll be 18 minus 36. And then once again, 1/2 times 9 is 4.5. So here, 18 minus 36 is negative 18. And then to get rid of the 4.5, you would have to divide both sides by 4.5. So negative 18 divided by 4.5 will give you the same answer of negative 4 meters per second squared. So as you can see, the answer for A comes out pretty consistent. Okay. All right, let's do part C. Part C wants us to find the average velocity for the first 5 seconds, meaning you go from 0 second to 5 seconds for the first 5 seconds, right? So there's a couple different ways to do it. Here we go. To find average velocity when A is uniform or A is constant, you can apply this particular function. The average is simply the final plus the initial, or initial plus final divided by 2. Well, what's my initial? I'm going to go to 5 seconds here. I know that at 5 seconds, the tangent line here is some sort of negative value, but I need to know what it is, okay? So I'm just going to go ahead and plug in what I do know and then just find what I need. VI here is 12 because we just found it earlier. The initial velocity at times equal to 0 is indeed a positive 12 meters per second. So it's telling us the object is initially moving to the right to begin with, right? We don't know what VF is. Well, VF at 5 seconds. I know some negative value here because the tangent line is negative. So let's go ahead and find VF. Well, to find VF, all you have to do is apply kinematics equation. The VF function here is just acceleration times time plus VI. Okay. The first strategy you can do is to go from 0 to 5 seconds. Well, if you go from 0 to 5 seconds, the time interval is 5. A is negative 4 because we already found it. Change in time here is 5 because I'm going to go from 0 second to 5 seconds. But if I start at 0 second, my VI here is going to be a positive 12 because I just found that in part B. Okay. So here we have negative 20 because negative 4 times 5 is negative 20 plus 12, which is going to give us a negative 8 meters per second. And that is our VF. Okay. Now, that is if you want to go from, 0 to 5, right? However, I like this vertex, and hopefully as you practice, you kind of figure out, what works best for you, okay? I like this vertex because I know with the vertex, the object came to a stop because the tangent line is flat, right? Which means I can start here and just go to 5 seconds. So the second strategy that you could use if you choose to, really using the same function, except I want to start at 3 seconds. But if I start at 3 seconds, my VI is actually going to be 0 because it came to a stop. But what's A? A is negative 4. How much time? Time is actually only 2 now because I'm going to go from 3 seconds to 5 seconds, which is a difference of just 2 seconds. Well, as you can see, this is way easier to do, right? Negative 4 times 2 is just negative 8. So as you can see, regardless of which strategy you use, you get the same final velocity at 5 seconds. You just have to be careful. Or not be careful. You just have to make a choice. Do you want to go from 0 to 5 seconds, or do you want to go from 3 to 5 seconds for this graph? I will choose 3 to 5 all day, because at 3 seconds the initial velocity is 0. Okay. All right. So once you have VF though, you can just plug it back into the average velocity function. Once again, 12 meters per second plus VF. We just found what VF is. VF is indeed negative 8 meters per second. So 12 plus negative 8 is a positive 4, and then positive 4 divided by 2, and that will give us an answer of positive 2 meters per second. And I highlight the positive sign because it asks for average velocity, which is a scalar, which is a vector quantity. Okay, so velocity is a vector quantity, so you do need to provide a direction. It didn't say magnitude, so I actually do need to give you a direction. All right. Now, if you didn't like the strategy and you want to go with this particular function, oh, by the way, in case you're wondering, average velocity is just connecting the two dots from xi to xf. So if you count correctly, watch my cursor. From here to here, that's 5 seconds. That's your run. And then up is 10, because from 10 to 20 is 10. So 10. So if you do slope, 10, 10 divided by 5, which is 2. So the slope there is 2 meters per second. Okay, or positive, because it was a positive slope. As I was saying, if you didn't want to do this strategy, you can really just exercise average velocities to go to displacement over time. If you do this method though, you need xf and xi, but xf and xi can be calculated super fast, right? Your xi is given, right? At times equal to 0, according to the graph, the object starts at a positive 10. So xi here is 10. Well, how much time? 5, because I'm going from 0 to 5. So all you have to do, the only thing holding you back really is xf. How do you know what xf is? If you look at this graph, I can eyeball it. Here, let me take this away. I can eyeball it. Here's 5 seconds, right? Where my cursor is. Here's 4, here's 6, right in between is 5. If I go up to the graph, it meets the graph there. And if I go left, it looks like it meets about at 20, but I don't know for sure, right? If you eyeball it, I would use 20 on an MCQ. But for an FRQ, I would write your workout and prove that it actually indeed 20. So I'm just going to show you how to do that real quick. Well, I drew that purple line, and I want to call that about 20. Okay, and so let me prove to see if it is 20 or if it's come out close or something close to it. So I'm just going to use my displacement function because I know a bunch of information already. Okay, well, delta x can be broken up into xf minus xi. Here xi is being 10. My vi already found that's 12. So look at this graph here, right? My vi, I proved it already that it's positive 12 because there was initial movement to the right to begin with. My time interval here is 5 because I'm going to go from 0 to 5. A here is negative 4. We already calculated that. And time here is 5. So if you clean all this stuff up, on the right side, 12 times 5 is 60. And then here, 5 squared is 25, right? And then negative 4 times a half is negative 2. Negative 2 times 25 is negative 50. And then negative 50 plus 60 is a positive 10. And then here, to find xf, you need to move this negative 10 to the right side. So therefore, xf is going to equal to 20, which actually does check out that it does indeed intersect this graph here nicely at that corner. Okay. All right. Now, if you don't like this, you can also do this, right? So if I did this strategy, I went from 0 to 5 seconds. Well, what if you want to find the position at 5 seconds, but if you start at 3 seconds? Same starting point, except if I start at 3 seconds, my VI here is going to be 0, okay? Because once again, the peak of this graph tells you the object changed direction. So it has to come to a stop, right? So if I start at 3 seconds, my VI is 0. Well, same strategy. Delta x is broken up to xf minus xi. But you have to be super careful. If you change your perspective, your initial position also change. So check it out. On the graph, if I start at 3 seconds, if I go to the left, that's 28. Or if you look at the coordinate system that's given here, that's 3 seconds, and at 3 seconds, the position here is 28. So the initial position is actually 28, not 10, right? So pick a perspective that works best for you and don't make false assumptions. All right. So A here is negative 4. T here is just 2 because I'm starting at 3 and I'm going to 5. So 3 to 5 is a difference of 2 seconds. So if you clean this up on the right side, what is this? 2 squared is 4. 4 times 4 is 16. 16 times a half is 8, and it's negative because there's a negative sign there. And then once again, to solve for xf, you would just need to move this negative 28 to the right side. So therefore, it would just be negative 8 plus 28, which would give you positive 20. As you can see, the values check out, right? If you did the first strategy from 0 to 5, it checks out. At 5 seconds, the object's at 20. If you did from 0 to excuse me, if you did from 3 to 5, it also checks out, okay? So it's very consistent. So if you do the stuff right, things will check out. Now, back to average velocity. If you wanted to take this route, you had to find XF. Well, I find XF to be 20, so I'm just going to plug and chuck. So XF is 20, so 20 minus 10, which is a positive 10, and then 10 divided by 5, which is a positive 2. So as you can see, the answer comes out to be the same, okay? All right. Listen to it, make a choice, pick a perspective that's comfortable for you, and then stick with it. All right, let's do D. D is pretty light. To do average speed for the first 5 seconds, all you have to do is find distance divided by time. So average speed by definition is distance divided by time. Distance is a scalar quantity. So here on the graph, I'm just going to go from 0 to 3, and then I'm just going to go up. So that is a distance of 18 because the position at 0 is 10. At 3 seconds, it stopped at a position of 28. So from 10 to 28, that's the distance of 18. And then I'm not done yet because it wants for the first 5 seconds. So I need to go from 3 to 5. And then from 3 to 5, it went down back to 20. So it went from 10 to 28. And then from 28 back to 20. Okay, so from 28 back to 20, it's a difference of 8. So, but distance is a scalar, so I just need to add everything up. So it'll be 18 plus 8. So here I'm just going to plug it in, 18 plus 8, which is 26, and then 26 divided by 5 seconds is 5.2 meters per second. I just noticed here, this should be 5 seconds. I forgot, but if you're keeping up, the term on the bottom is time. So just add the S unit there visually for me. Okay, so that is our answer for part D. Okay, now let's do part E. Part E wants you to find the instantaneous velocity at 8 seconds. Well, to find instantaneous velocity, which is the same as finding the final velocity, well, you need A, you need T, and you need VI. So here, I'm actually going to start at 3 seconds. Once again, if I start at 3 seconds, my VI is going to be 0. I'm just going to go from 3 to 8 seconds, okay? A is -4, and then my time here is actually just going to be 5. I know the question says 8, but I'm starting at 3, and I'm going to 8. 8 minus 3 is 5 seconds. So -4 times 5 is just -20 meters per second. Or you could if you want to, right? Because you just have to make these choices. I just took it from 3 to 8 because I can cross out VI, because VI at 3 seconds is just 0 because it came to a stop. Or if you want, you can just take it from 0 to 8. If you apply the same function, but if you want to take it from 0 to 8, you just have to be consistent with your time interval. A is -4, that you cannot change for this problem. T here is 8 seconds because you're going to start from 0 to 8. But if you start at 0, your initial velocity is actually 12 meters per second, right? And we established earlier, the object was initially moving to begin with at 0 second. So what was that rate? We calculated to be 12. So if you do this correctly, right, -4 times 8 is -32, and then -32 plus 12 is going to be -20. So as you can see here, the answer comes out. But for this one, you went from, or I took it from 0 to 8, okay? So make a choice, practice, and then stick with something that makes sense to you, okay? All right, stay nerdy, don't be whack.